Hello, everybody. Welcome to this is the second to last PBL, so this is PBL 11. And today we're going to go over this whole ICU problem here. I'll let you read over this, but I'm pretty sure that the scenario here is something out of Grey's Anatomy, which my only hint here is this Meredith Grey character, and I know Grey's Anatomy is a show. I've never actually seen it, but maybe Chris has, and maybe he really likes this. We're actually going to start halfway through the document. There were some conceptual problems before this, but since they were purely conceptual and even the rest of these are pretty conceptual, I just wanted to start halfway through. But go ahead and give this a read and then we'll get started. All right, so here's question one, or I guess problem five in our case. And I'm just going to blow through these pretty quick. I'm not going to do a whole lot of writing. I'm going to do a lot more talking. My handwriting is not as good as my math is. But the first thing it wants us to list at least four sources of energy entering the ICU. If you go up to the previous document, we've got ventilators, monitors, warming devices, metabolic heat of staff and patients. So those are four things adding to the ICU already. Question two asks us to list two ways energy is leaving the ICU. And so we have the HVAC system here. I didn't see another one as I read through it, but it would, it would naturally kind of leak out through the walls, through doors as doors are open. So heat would also just naturally leak out because it's colder outside than it is inside. And so heat wants to move to where there's less temperature. To sketch this, I'm going to do a very basic sketch here, but let's say that this is the ICU flowing in. We had four sources that we chose. So these four sources would be the ventilators, monitors, warming devices, metabolic heat of staff and patients. And let's say that there's two sources coming out here. And that's pretty much it for all major energy inputs and outputs. You can label each of these arrows if you'd really like. Explain why ICU temperature rises when energy enters faster than it leaves. Include relationship between energy, temperature, and energy balance. So the net thermal energy of the air and objects in the room is increasing because there's more energy coming into the ICU than it's removed. So I like to think of it as these four arrows are coming into here and they're existing in this space, and then only two arrows are pulling them out. That drawing probably didn't really help a whole lot, but I imagine that if you could think of it in terms of a balloon, if you have a balloon with two exits or two holes in it, and one hole is connected to a really fast moving air pump, and the other one is just a very small hole which air will naturally leak out of. If the air pump is moving fast enough, then the balloon is still going to blow up faster than the little hole can bring the air out of it. It's kind of the same thing happening with the energy here. Okay, question five. Why can even a small but sustained imbalance in energy flow produce a noticeable temperature change over time? This is pretty obvious, but if the difference between the inflow and the outflow, so I'll go ahead and label this. This is in and this is out. If it's a small, it's in one moment of time, it's not that big of a deal. But if it's continuous and sustained over, hours and hours of time, then eventually there's a whole lot of temperature and heat building up in the ICU here. You would mathematically, if you were to do this, you would integrate the change over time. And then ICU and a small supply closet are both at 26 degrees Celsius, which contains more thermal energy. Again, relatively obvious. The answer is the small supply closet because, well, it's smaller. Even though they're at the same temperature. Sorry about that. That is, I'm pretty sure, the third time that I have forgotten about my 8 p.m. alarm while I'm making one of these videos. Anyways, the energy in the supply closet is greater. The ICU has a larger volume, so it contains more air and more object, and it takes more overall energy to heat it to 26 degrees. And then for question 7, engineering team turns off non-essential heat producing devices. How does this change temperature trend in the ICU? We can't really answer this fully because we don't have numeric values for anything, but assuming that the heat producing devices, let's say that there's 3 heat producing devices we can erase here, then the heat would decrease. We got 1 arrow going in and 2 coming out, assuming they're all the same numerical. If we still had 2 arrows going in and 2 arrows going out, then it would stay the same. And 3, it would still continue to increase, just at a slower rate. Okay, for problem 6 now, all of these questions are going to be based off of delta U equals Q plus or minus the work. So for ICU as a closed system, list the major sources. Again, I'm just going to go back to these same sources. So ventilators, monitors, warming devices, and metabolic heat. And then question 2, list main contributors to Q out. That's just going to be the HVAC system. And it looks like Krish has actually listed them for us. They're the HVAC, heat removal, and passive cooling. I can't think of any other main contributors to that. So thank you, Krish, for that. He did say this one was going to be pretty easy. Anyways, meaningful mechanical work done on the system. The answer is no, because for mechanical work, something has to be moving, and the only thing moving is the air. So mechanical work would be like if the ICU itself was on a big shaker plate and was shaking uh, vigorously, then be it'd be quite a bad situation there. But that would add some work to the system. Using first law, explain why ICU's internal energies increase when heat is added. So with the first law, you can say that delta U also equals Q in minus Q out. So since Q in is bigger than Q out, we have, I'm trying to think of in words how I want to say this, but basically there's more energy coming into the system than there's energy coming out of the system. And connecting internal energy to particle motion and temperature, well, the internal energy is going to cause particles to move faster and temperature to rise because of that. And then for the generator room itself, if we're just looking at the generator room, it says major sources of thermal energy added to the space. Well, the biggest one is, of course, going to be the generators themselves. They're going to be, something is happening to fuel the diesel engines, and that's going to cause heat. There's going to be waste heat coming off of the engines. That's going to happen. Maybe if there's friction in the moving parts, that's going to add to it. If there's a cooling system, that's going to add to the energy. So there's a lot of different things you could nitpick and say. Explaining how increased internal energy reduces generator efficiency. So, as the temperature in the generator room rises, this is going to affect the generators themselves. Like, if it's just looking at the generator, we just have the temp of the generator and it's operating at a consistent thing. But as you add the temperature of the system, then our total temperature is greater. And since the total temperature is rising because the temperature of the system is rising, temperature total is rising, temperature generator is going to be rising because it's been on for a long amount of time and the heat around it might be affecting it. This is going to decrease the efficiency of it. Question 6 here is, I think, the most important one here, but it asks us to classify what it does. So turning off non-essential heat producing devices, it's going to decrease Q in. And then increasing HVAC removal capacity is gonna increase Q out. And then reducing generator load is going to, well, in regards to the ICU, let me think. I guess it kind of does both. The generator room is going to, I think it changes both is the best way to describe that. But which strategy most directly reduces delta U in the ICU and most directly reduces delta U in the generator room? Well, for the ICU, you could argue that either of these most effectively reduce delta U. It just depends on how much they either decrease the energy in or increase the energy out by. And obviously, reducing the generator load by closing non-critical units is going to most directly reduce delta U in the generator room because we have um, Q in for the generator room is decreasing. Okay, problem 7. So now we're going to look at some actual numbers. So we have the generator receiving 750 kilowatts fuel energy per second and delivering 225 kilowatts. The first question wants us to define the efficiency, and then I don't know what's happening here, but I assume that Krish is just looking for eta of the heat engine and write its expression. So the expression for this is going to be P out over P in, and I'm just going to give that to you guys. Um, but this gives us the efficiency of a heat engine. And so we have, for our values, we have 225 over 750, and this gives a value of 0.3. And so for question 2, the normal efficiency is 0.3 or 30%. And then question 3 wants us to answer how much power is rejected as waste heat. The answer for this is just going to be the difference between P in and P out. So if you do P in minus P out, that's 750 minus 225, and this is 525 kilowatts. So I'll put that down here. Where does it go inside the hospital, and why does it place additional load? Well, directly it's going to go to wherever the waste heat from the generators is expunged, but if we assume this is just inside the generator room, and the HVAC system is relied on to remove it, then it's going to go all throughout the hospital because uh, it's going to go initially into the generator room and then kind of seep through the walls and through the doors because the HVAC system isn't operating at very good capacity. And then during the storm, our output drops to 180 and fuel input remains at 750. And so if we do set 180 over 750, we're now operating at 24% efficiency. Decrease in efficiency means a larger fraction of fuel energy becomes waste heat. Well, you could just calculate it exactly if you wanted to. You could do the new P in minus the P in remains the same at 750, but the new P out. So 750 minus 180 is going to give us now 570 kilowatts instead of 525 kilowatts as waste energy, which is obviously going to worsen the thermal problem because more energy is going into the system. And then no real heat engine can be 100% efficient because there's always going to be some form of waste energy. The system has to move, and that is going to produce some form of heat energy. And then why must a hospital rely on both efficient generators and efficient heat removal systems? I feel like that's relatively obvious just from the numbers we have crunched. Uh, in our box example earlier, when we drew it with this being the ICU, efficient energy generators would be like two arrows coming in and two arrows coming out, so that the overall temperature in the ICU just remains the same. Okay, last question here. Now we're going to look at the HVAC system. We have that it's removing 600 kilowatts of energy and drawing in 150 kilowatts of energy. The first question wants us to define the coefficient of performance. The equation for this, again, I'm just going to give it, is just Q out over P in. And then if you calculate this, 600 divided by 150, the coefficient of performance is 4. And then during the storm, the coefficient of performance drops to 2.5. If we have the same 150 kilowatt electrical input, we need the new Q out. So here we have Q out over the same input. So 150 equals 2.5. So you just multiply 2.5 by 150, and you get that Q out equals 375 kilowatts. By what percentage or fraction has the cooling capacity decreased? So we have, well, to do this, we do the difference between them and then divided by the initial value. So you would essentially do, Q1 minus Q2 over Q1, which is 600 minus the new one is 375 over 600. And this is 0.375, so 37.5% decrease in efficiency. So in other words, it's at 62.5% of its original capacity. So we have, I'll write it here, 37.5% decrease, so down. And then why does a drop in the coefficient of performance make the HVAC system seem to struggle, even though electrical input stayed the same? Well, you can see that with our coefficient only being 2.5, the amount of energy coming out of the system is lower now. Question 6 now. Internal heat generation totals 550 kilowatts. Under normal HVAC performance, does the system remove enough energy? What does this apply for long-term temperature? Well, normally it removes 600 here, and it only produces 550 in this case. So it removes more energy than is necessary. So really the heat is going to decrease. They're going to have to turn on the heat here. And then let's see. Under store, what does this imply for long-term temperature? Just means temperature is going to drop unless they turn on the heat. But it's going to be relatively slight. Under storm conditions, is the internal energy of the temperature increasing, decreasing, or steady? Well, under storm conditions, we have 375 kilowatts being taken out and 550 being produced in the system. So it's going to increase. There's not enough coming out. More heat is being added than removed. Internal energy and temperature is going to increase over time. Why does the ICU continue to warm even though the AC is running at full blast? I mean, kind of just exactly how we said it. Even though it's running at full blast, it's at full power. It's only removing 375 kilowatts, and there's 550 kilowatts being produced. So it's not going to take enough out. And then why all real heat pumps have an upper limit on the COP? and why cooling mode becomes harder, not easier, when the outside air becomes extremely cold. I'm Let me think about that. Well, as the outside air becomes very cold, the heat pump has to pump heat across a larger temperature distance. There's, inside the building here, temperature may be 26 degrees, but if it's really freezing outside, then it's 0 degrees out here. I think that's in Celsius there. It's not freezing in both places. And this is a huge difference that it has to overcome. And so the process is a lot less efficient. And then summarize how reduced COP and increased waste heat combine to drive a thermal cascade in the hospital. I think that's pretty much just summing everything up. We found earlier that the total heat in the system is increasing, and the from this problem, we see that the reduced COP is removing even less energy from the system. And so energy in the system is increasing over time, and everything is just getting hotter. It's all very bad. Uh, Thanks for watching this video. It was a more conceptual one, but I hope that you enjoyed it. At the very least, I'm thankful to Krish, as always, to making these videos for us, and I wish you luck with all of your finals that are up and coming.